Cool. All right. So, Matějek, would you like to introduce yourself, or should I do it for you?
I guess I'll introduce myself, but if you have something nice to say about me, you can, I guess.
It's just I think we haven't seen each other for quite a long time, so I would just read what's written in the event. I just wanted to say to everyone, welcome to Pivo, to Virtual Pivo again after a few months, unfortunately. But the good thing is we can have guests from other towns, cities, countries, whatever. So, well, cheers to all of you. Welcome back, and let's see what Maciejczyk wants to tell us and share with us.
So, hello everyone. My legal name is Jan Matějek, which is written in the synopsis, and I use the name Matějčík almost exclusively on GitHub and everywhere. I apparently set up some animation here and I forget about it, so let's see if it comes in. So I've been programming for quite a long time for money in Python, and in MicroPython, I'm working the last 4 years for Satoshi Labs, the company that makes the Trezor hardware wallet. And this is the full slide. And thank you, Jirka, for letting me speak here. And I would like to show you something about MicroPython and Rust and what I do at my job right now. First, little about MicroPython itself. What is MicroPython? It's an Python interpreter for microcontrollers, so like chips like STM32, and it's not a dialect, it's not a modified Python, it's actually the full-size language. It supports something between Python 3.4 and 3.10. I believe they're claiming full 3.4 support and some select features from the higher versions. And because it's not a dialect, it brings some specific problems because Python is a very strong language and very dynamic language, and you can monkey patch anything at runtime. And it presents some unique challenges, as we'll see later. MicroPython, unlike the desktop Python, has a garbage collector based on the mark and sweep algorithm, which is nice and fast for as long as you have enough memory. And once you start running out, it starts getting slower. The implementation is nice, memory space efficient, etc., etc. And it's quite fast for a Python, but for a Python, it's not too much so. About Rust, I actually don't know that much about Rust. I started working with it about a year ago, so I'll just tell some things that seem important for me. Maybe someone will say more. It's a low-level language on the level of C, basically, but it offers some very nice abstractions. It's some functional things, some zero-cost abstractions, which is pretty cool, things that compile down to very fast code, but are very expressive. It's very modern, very new. The compiler is super nice, awesome error messages, point you to the documentation that tells you how to fix the error, etc., etc. It's super fast because it runs on bare metal, compiles down to machine code. And the most interesting thing for us about Rust is that it's very safety oriented. It has this crazy thing called a borrow checker, which basically at compile time ensures that there are no memory errors in your program. And you can avoid it by using unsafe code, and we need to do that quite a lot. But as long as you're keeping unsafe out of your programs, you can be sure that there are no bugs. Of course, no bugs ever. And there's the coolness factor. Everyone likes Rust, so this is the Trezor Model T. It's our hardware product. It's a hardware cryptocurrency wallet. In real life, it looks like this. I'm showing it on camera. It's a little USB device with a screen. Inside it is STM32F405, I think, microcontroller. It has 1 megabyte of flash storage and 192 kilobytes of RAM, which is not a lot, but we can and do run MicroPython on it. And our project is pretty large. It's like 74,000 lines of code, which is one of the larger MicroPython projects out there. And we actually run into the problems with memory, as I will show later. And of course, the project is completely open source. Everything is on GitHub, including the hardware schematics, full sources of the firmware. And we love open source. And we think that like doing cryptocurrency wallets via open source code is the best way, the only auditable way, and the only way to trust that the hardware is doing what you want it to do. And we are currently solving some problems with limited memory and limited CPU power. So we need the thing to go faster. And that's why we chose to extend MicroPython with Rust. The reason to choose MicroPython in the first place is that it's a nice abstract language, and it is also by itself memory safe. So we don't have to worry about memory errors as long as the MicroPython interpreter itself is okay. And so far, it's been okay. We haven't found any problems, which is amazing. But like on the other hand, it's huge, so probably there is something if you look hard enough. And Rust has the same property. It should allow us to not write any memory errors, any exploitable problems. Because the hardware wallet is a security-minded product, we really don't want any use after free and shit like that. About this talk, I will be talking about implementation details of MicroPython, which are done in C, about API for extending MicroPython, which is also C, with interoperability pitfalls, which also concerns C. So it's a very low-level thing. Another thing I want to say is that most of this was invented and written by my colleague Jan Pochela. And my screen disappeared somewhere.
Sorry.
Okay.
I thought. Can you try again, please?
I can't because it says I'm not allowed.
All right. Let's try now.
Yes, that's nicer.
Okay. Sorry about that.
Yeah, great. Wonderful. Yeah, so this was not designed by me. I'm just presenting it. And everything you see here is a work in progress. We started using Rust like 6 months ago in production, and we are still developing a lot of things that we'll need in the future. So it's not done yet, and there are probably better things to do, better ways to do things, etc., etc. So let's get to it. First of all, MicroPython internals. The thing that concerns us the most is not the interpreter itself, like bytecode. I don't care about bytecode because I'm not interacting with bytecode. I'm concerned with the garbage collector and the data structures in memory. As I said before, the garbage collector is mark and sweep. That means that whenever you want to collect garbage, you start from some known objects like the module globals, etc., loaded modules, and then you walk the whole memory space and follow every pointer, and whatever you find, you mark. And then you walk the whole memory space again, and if you find any unmarked spaces, then you collect them and you free up the memory. This is reasonably fast if you're doing it on like when not much memory is consumed, and it gets slower the more memory is consumed, obviously. We have allocation in 32-byte chunks, so the smallest piece of memory that you can allocate is 32 bytes. And if you allocate more, then you are not allowed to point inside this memory, because the garbage collector will not understand the pointer and will ignore it, and the memory will get collected wrongly. This also means that the pointers have some lower bits that are free for all, that can be used for something. because if it's not a round 32-byte pointer, then it's not a valid pointer. So what MicroPython actually does is use these lower bits to stuff some more information in there. There are special values that can be placed in a place of a pointer, and it's a constant. It indicates Python's none or true or false. There's an indicator that the pointer is in fact a number. So you cut off some lower bits, and the rest is interpreted as a number smaller than, I don't know, 2 to the power of 30 or something. And the specialty is called a QString, which is an intern string. I don't have a slide for it, so I'll just talk about it. And instead of storing a string for everything, there's a lot of string in Python. You know, every method name is a string, every variable name is a string. You can use getUtter, setUtter, and all the keys are strings. So you need to remember as a string everything that's in your program. And in order to not spam the memory with these strings, there's a huge lookup table of strings that are collected during runtime. And you can, instead of the string, you can just set the index into this table. So instead of a pointer to a real string, it's just a number, and you look up the number in the table and see what's it supposed to say. So we know how to store the constants, true, none, true, false, none, very small integers, and QStrings. And if we need to store something larger, like a real string or an object of any kind, we need to actually allocate memory. And we get a GC aligned pointer, one of the 32-byte blocks. And in C, it looks like this. Zoom in. So is this readable? Is it okay? Should I make it larger?
It's okay for me.
It's fine.
Okay, great. Thanks. So the first item of this struct is MP object base T, and that's a pointer to the object type. I will show you how the object type looks alike in a minute. And the other items are things that the object contains. There's a special type that describes Python object. This is implementation of the string object. And the type object itself has a lot of things. Because it itself is an object, it has to have a pointer to a type as its first item, and then have some flags, then its name. You will notice that it's not a string, it's a QString. It has some function pointers for printing, for a constructor, for invoking it as a call, for some operators, for attribute access, etc., etc. So if you want to write a Python object in C, you have to create this struct for type and set up some callbacks, and then MicroPython will call your C function when, for example, the programmer wants to call the object, wants to call something parents and parents, then this will get invoked. So what are the limitations? Our biggest limitation is memory. I also already said something about this. So the first problem is that every module that you import is a dictionary in RAM. Why? Because you have monkey patching, you have setUtter, you have access to globals. So you need to be able, in order to support the full Python language, you need to be able to modify modules at runtime. So whenever you say import something, then the something module is created in RAM, and there's a dictionary of all the names and the objects that are stored there. And this dictionary is modifiable by Python functions and by C functions and by whatever. Every single function defined in the module is also an object in RAM, because every function has a reference to its globals, and the globals is a live dict. So in order for this to work, you need to allocate the function object also in RAM. This is fortunately just a very small thing. The code of the function, the bytecode, is stored in the flash memory because it's not modified, but the function object itself is live. And when we have a very large project, 150 modules, 10 functions per module, that's 62 kilobytes just for existing, just after loading all the imports. And that's out of the 160 kilobytes that I and we would like to bring this down somehow. One way to bring it down is not write modules in Python and write them in some other language, maybe Rust, you know. This is how a memory map looks like. I will open the HTML. I will send you a link to the chat. And I'll zoom in a little. The file is huge, it's like 3 megabytes. It's automatically generated from some function that I wrote. And zoom in a little more. So each character in this map represents one GC block. And the B is function. The equal signs are continuations of the block. So this one is a location that is this long. It's some sort of buffer. I don't remember which. And I can click on it, and it will tell me that it's a raw buffer. It's some memory that I have allocated, and I don't know what's in it. If I click here, I see its function. What's its name? It allocates 2 blocks. This is from the emulator that runs on Unix on PC, and on the emulator every function takes up 2 GC blocks, but on the real hardware, which is 32 bits, the function only takes 1 block, so that's nice. And there's a pointer to its globals, which is some sort of module, and there's a map of properties of this module, and it's pretty long. If I click here, it will point me back to the memory map. And this is how the map looks like when running some difficult workflows like signing Bitcoin transaction. You can see that there's a lot of dots, which represent free memory. And so you can see that the memory is pretty fragmented. Because the GC works linearly, and when you want to allocate a block, it just finds the first block that's large enough and will skip over blocks that maybe are allocated at that time and they maybe get freed later. So it would be super nice if I had some sort of defragmentation method and to shake down the memory and get all filled space at start and all free space at the end. But unfortunately, it does not work that way. And second, very related item that is limiting us is the speed of the garbage collector. Mark and sweep is nice, but the more objects you have, the more work it takes to walk through all of them, jump all over the memory, and find everything. I'm sorry. And find everything that should be collected or not collected. When you try to allocate some memory, the search is linear, so the more memory is full, the more time it takes. And unfortunately, we have very little control over memory fragmentation. And that's because every little thing is an allocation. Like when you create a tuple, it's an allocation. When you add 2 lists, it's an allocation. When you add 2 strings, it's an allocation. When you create a generator, it's an allocation. When you destructure a thing, it's an allocation. When you index into a string, it's an allocation. Basically, every other operation in Python is an allocation. So we have it awesome when programming on desktop because we don't really worry about these things. When I have 256 megabytes of RAM, that's so much. And here I need to really worry about it. And this means that as more memory is used, I need to garbage collect more often, and it takes longer and longer, and everything crawls to a halt. So that's something I'd like to avoid. For example, by getting better control over how the allocations work, maybe in a lower level language, sort of like Rust, maybe. Let's do it. So First of all, to extend MicroPython, you have to use the C language. There's a pretty nice API for this, a lot of useful functions, a lot of useful macros. So what I'm going to do is I will interoperate first from Rust to C and from C to Rust. And then I'll use MicroPython's C API to interact with Rust directly. If I want to call C functions from Rust, I can just use the bindgen tool. It's very nice. It's a tool, you point it at C header, and it will generate a Rust source file with all the functions. I think I have an example somewhere around here. Oh yeah, I have to share something else for the example. This one. This is how bindgen generated file looks. There's some structures and type redefinitions, and if I scroll down, more structures and some functions. And this is basically what a C header would look like if rewritten to Rust. So nothing more complicated than that, but it's nice that we have a tool that does this for us automatically. So I can just take the MicroPython headers and convert them to Rust headers.
And screen share is gone again.
Yeah. I'm switching to a different window,
Right,
so
sorry.
I need to turn it off and on again. Thanks, though. This is my presentation. Yeah. So this is nice. Calling Rust from C is a little more difficult. There is a C bindgen tool which does the opposite job of bindgen and generates C headers from Rust, but we're not using it. I'm not actually sure why. I think it's overkill for our small project. We are exporting like 10 C functions, so it's much easier to just write a header manually. So this is how you define a function in Rust that is callable from C. You must use the nomangle directive so that the name is not changed when compiling, and you have to use extern C so that the C calling convention is upheld. And then you have the name of the function, arguments that are C compatible, and then you write a custom header which has the signature of the function, looks like this. So this is my function, returns MP object T and has the same arguments, except it's in C language now. It's the same language level, so it's just a matter of telling one language to understand what the other language wants to it. There's no difficult job on it. Now we have the job of calling C from Rust, Rust from C. Now we want to call from MicroPython or to MicroPython. So first of all, we create a module. Looks like this. This is some sort of map, which I call global stable, and it's a list of pairs. This is definition of a QString. There's some build magic behind it, and this will be the dunder name item, and it links to the name treasure utils. This is the name const_eq, and it links to some sort of pointer to some sort of function, etc., etc. And then I define MP object module T, which is called something. Its type is module. This is the first item because module is an object, so I have to set the first item to its type, set its globals, do that thing that I just created, and then I call a macro that will register this. And once I have this done, I just import it in Python like this. And that's it. That's very easy as long as you have the functions ready. Yeah. Now the Rust side. I would like to accept arguments from MicroPython, and the trouble is that MicroPython treats everything like MP object int, and Rust likes to have its types like more precise, like know if it's an int or a boolean or a string pointer, etc. So this thing can be a GC pointer to an object that I've shown before, one of the smaller constants, and we created a wrapper around this thing. We call it obj, like an object, and it looks basically like this. I have a bunch of functions that test if it's something special. For example, if it's small int, if it's a Q string, if it's a pointer, if it's null, yada yada. And then I have a long list of try from implementations, which is Rust's thing, Rust's way to intelligently convert between data types. So impl try from object for bool means that at some other place of code I can write something dot try into and get a boolean value out of it. And how it works is I will call an unsafe function called mp_object_is_true. This is a MicroPython function, and it does this intelligent thing, like if the object is the true constant, it returns true. If it's the false constant, it returns false. If it's an empty string, returns false, etc. If it's a user-defined object, it will call the dunder_bool method so that the object can do its own processing. This means that mp_object_is_true can raise an exception, so we have to wrap it in this catch exception function, and then I get back the is_true value. And I'm using the question mark operator, which will do some magic and convert the result into an error if there was an error. And I will return that it's okay, or otherwise the error is returned automatically through the magic of the question mark. And I have this for Boolean, for various types of integers. Then I have the opposite. I have conversion from Boolean value into object, which is trivial. If val, we return the true constant, else we return the false constant. It's a little more difficult for some of the other types. So this is basically how to handle the objects that come in from MicroPython. We have some wrappers. I'm getting to the 20-minute mark, so I won't be showing each of them, but we have a buffer wrapper, which allows us to read strings and bytes array. We have iterator, which implements the Python iterators in terms of Rust iterators. We have the map type, which is universal mapping. We have some specific things like lists and dicts. We will be adding more if we need them. And taken all together, it looks like this. I will show it on GitHub because it's a little prettier. It would be nice, right? So I declare my variable as type of buffer and extract it from the QArgs, which are of the mapping type. I'm asking for the title and doing try into, which will convert it to my type. There's some option, so it can be none, etc., etc. There's some Boolean, so I'll just do the same thing. And at this point, I have this whole block of variables that are correctly typed for Rust, and I can call some Rustish functions and do stuff with them. And that's basically it. There's a lot of pitfalls that I haven't mentioned, and I might mention them later, but I believe that getting into them right now would be too deep, so maybe in the discussion afterwards. One thing I want to talk about is the garbage collector. We are using Rust with a no STD, so we don't have the standard library, we don't have Rust's allocator, and even if we did have it, we cannot use it, because the allocator cannot guarantee safety from the MicroPython allocator. If I create an object and allocate it on the Rust heap, if I did it separately from the MicroPython heap, then I would call into MicroPython, and maybe MicroPython would never call me back, and I would have a memory leak because there's nothing that frees the objects on the Rust heap. So we need to use the MicroPython garbage collector, and that means that we need to have a custom allocator. Instead of box and vec, we have this GC for specific types. You can allocate it, and it calls into the allocators and returns the memory. And the implementation is actually very simple. It's, I don't know, 50 lines of code, but it's super unsafe because there are very no guarantees. MicroPython can call me and give me the same object twice as an argument, and I have no good way to figuring this out. I have to be careful not to do interior pointers, because if I do, I must keep pointer to the head of the allocation. Otherwise, my interior pointer is ignored and the allocation is lost, and there will be errors. And so we have a lot of comments that describe safety of using each function, and we have to be careful, at least at this boundary. Some results. At first, we rewrote the protobuf codec, which is something that we use to communicate over the USB. And after rewriting into Rust, we get 5 times speed up, which is nice because it's still not super optimized. It's still creating Python objects and returning them. So it's still involving some allocations, and it's still 5 times faster than it was before. Right now, we are implementing the UI toolkit, which is great for us because the UI toolkit is very big in terms of lines of code and in terms of module size. So just by rewriting to Rust, we gain memory because it's not in Python, because we don't have to import the Python modules. And it's looking very promising. It's very nice to program in, but it's not done yet, so I can't talk about the results too much. And of course, happy programmers, because Rust is fun, and because it's something new to learn. So I guess that's it. One last thing, we are hiring. So if you would like this to be your day job, apply at Startup Jobs on our page. And this is a space for questions. So I hope you're not overwhelmed. And even if you are, feel free to ask me anything. And thank you for your attention.
Ooh, clap, 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 clap. Thank you very, very much.
Thanks a lot, Matějek. That was great. I see no questions in the chat. So if you want to ask, you can, again, well, if you're shy, you can use chat. If you want to go on cam or on the mic, please ask directly.
So I have a question. That means that you are probably the first one we know that uses Rust in production.
Right.
Are you using Rust? It means that you're using Rust.
Yes, absolutely. We released firmware that uses Rust, that uses the protobuf codec sometimes in summer. So it's already on devices that people own and use every day, and it works fine, and it's great.
Do you see any, let's say, gain in interest in the amount of developers that you're getting? Oh, and we are using Rust, not only.
Unfortunately, no. And I think it has to do with the fact that we are developing a hardware wallet, and the vast majority of interest from developers are people who want to implement new cryptocurrencies. And this is a very specific group, and it's very different from the group who would enjoy Rust. So no uptick in interest so far.
Shame. Cool. So do we have any other questions from the public?
Oh yeah, Python exception, Rust results. Exceptions is a fun topic because MicroPython implements exception as long jumps, non-local returns, and Rust does not do that. So if you do a long jump from a Rust code, then you skip some finalizers and can break all sorts of things. So we have to do this while thing where we have a very small C wrapper that sets sets itself up as an exception handler and returns the result to Rust as a return value. And then, as you say, we convert it to result and bubble it through the stack. And then again, at the boundary, we convert it back to the Python exception and call the non-local jump when we are about to return to Python. So yeah, that's amazing. Do you use stable Rust toolchain? We were using stable Rust up until now, and we now have a developer implementing Zcash in Rust. And unfortunately, they need some nightly features, so we will be probably switching to nightly. It's not custom toolchain, it's just upstream nightly because there are some features that we need that are not in stable yet. Jake, you are muted.
That's happening quite often to people while talking online. Anyway, while being on Python Meetup, can you briefly describe, let's say, key differences between standard Python and MicroPython?
There isn't many, actually. I mean, it's almost the full thing. The one thing that doesn't really work that well is metaprogramming. And the descriptive protocol for class members, but I believe it can be enabled by some configuration option. What doesn't work is slots, which we would love because that would save us memory, but it doesn't work. And some specialties like the slicing operator, which skips different than -1. Like if you want to select every other element of a list, you cannot do it easily by the slicing operator. And yes, the C API is different. But other than what I said, the main difference is that you don't have the standard library. The language itself is amazingly complete. We do stuff like custom implementations and dunder methods and decorators and, well, anything really.
And in this project, did you start right away with MicroPython, or you had different versions of Python before?
Yeah, so the Model T, the hardware wallet that I'm talking about, is written in mostly MicroPython from the start. There are some C modules for things like controlling the USB and some low-level rendering functions, but really the most of it is written in Python. And this was like this from the start. We had one older model, the Model 1, that's not as advanced, and it was all written in C. And the decision was made to start from scratch in Python, in MicroPython for the new model, because it's going to be nicer, because it's we will be more productive as developers, and it will be safer. We will achieve memory safety.
Nice, thank you. Do we have any other? There's one.
We are using async and await, but we are not using usync IO. We have our own implementation of the reactor or runner, or I am not sure what it's called. So the event loop, basically. So yeah, a lot of the functions we do are async, but it's not usync IO. It's a custom thing.
Any more questions? 1, 2. No.
Async functions in Rust. Not yet. We were thinking about mixing MicroPython's async and Rust async, and it probably will not work. And Rust's async is quite unstable right now anyway, I think. And at this moment, we are not sure how to write async functions like MicroPython async functions in Rust. And we don't need them currently. Whenever we need asynchronous, we just write a Python wrapper that calls into Rust. If we ever need it, we'll do the work and see if it can be done.
as always, offering any more questions. Well, probably not then. Matějek, will you stay with us for longer, or you're rushing away?
I'm quite hungry right now, so I'll probably go have dinner, but I might join later and see what the fuss is about. So
Okay,
yeah.
Perfect. So probably, if possible, then and more questions can be answered later on. Thank you very much for this.
Yeah,
and
thank you so
have a
much
nice
for
dinner.
having me here.
Thanks, Matějek. Pleasure.
Yeah, it was a pleasure,
Fun.
and hopefully we learned a lot.